everyone, welcome to this week's MathCast podcast. Today we are joined by an academic scholar and a Math Sleep student. We are joined to discuss Zeno's paradox. Without further ado, let's get started. Alright, just to start off, who actually is Zeno?
So Zeno was a guy from ancient Greece. He was a mathematician and a philosopher. Now, of course, we all know that ancient Greece was filled with mathematicians and philosophers. But what set Zeno apart is, unlike the most famous mathematicians from Greece, i.e. Pythagoras and Euclid, Zeno wasn't a hardcore geometrist. We all know Pythagoras for his triangles and Euclid for his circles and compasses, but Zeno was fascinated with something else. Paradoxes.
So he has many paradoxes which baffled the minds of many people and is sort of said to be complete or settled. But in reality, they're very fascinating to think about, and they actually hurt the brain a lot. So one of them states that motion is impossible. So we'll go about this by a bit of a different way. So I'm pretty sure everyone remembers these Lego stop-motion animation videos that we would all used to make when we were younger. So it would consist of many still Legos, and then we would take pictures of them, and then we put them together to make a video. And the more pictures you took, the better the video would be.
It states that motion is impossible because we're just moving through an infinite amount of still images of her hand just getting closer and closer to where she'll stop waving, and that just creates the illusion of motion. We're not actually moving.
Well, this was a paradox, but we all obviously know that motion is real.
Anyways, there's another paradox he had called the rabbit and the tortoise. It's about a race between the rabbit and a tortoise. Not the story from Aesop's Fables, okay? Not the story. Different times, guys. What happens is, the tortoise is half as fast as the rabbit, but the tortoise still manages to remain ahead because he gets a 1 meter head start. By the time the rabbit is at 1 meter, he's at 1.5 meters. And so on.
Yeah, so this is another of his paradoxes. So today we're going to be talking about a sort of simplified version of the rabbit and the tortoise called Zeno's paradox. And it's about if, let's say, you're traveling a distance of 2 meters. In order to travel this distance of 2 meters, you must first travel 1 meter. Hope you're all with me until now. So if we need to travel 1 meter, we need to travel half a meter, and so on until we have to travel 1 divided by 2 to the power of some
really long number.
Yeah.
Meter. So the concept of this is we can never actually reach 2 meters because the steps just keep getting smaller and smaller and smaller, and because numbers go on forever, our denominators for these fractions just keep getting bigger and bigger and bigger and bigger and bigger, and the steps just keep getting smaller.
Until we can't fully take 1 step because there's always half a step before that. So it's sort of putting this idea of infinity into a real life scenario where obviously we're going to travel the 2 meters, or obviously we're going to clap our hands. But in this situation, it sort of states that it's impossible because there's always half a step before that. So this is what we call a well-behaved sum, which has a limit. The limit is 2 meters because the sum of all of this is 1 plus a half plus a quarter plus an eighth plus a 16th and so on, and
it equates to 2. How can this infinite sequence end with such a finite number? Like, this is an infinite sum. Shouldn't it end with pi or e or a pesky transcendental number? No, it's easy to think about it if we think about it as decimals. So if we convert a half to 0.5 and a quarter to 0.25 and so on, we can look at it like this. We start with 1, then we get 1.5, then 1.75, and we just keep getting closer and closer to 2.
Yeah, so this is the limit. It has a limit of 2. So how can an infinite set of steps have a last step? So as we said, it's not even 1 step is going to be possible. But like Rhea said, it has a limit of 2 because you keep adding different fractions together and it equals 2. So I have a really fun story.
Yeah, if you're not convinced that it adds up to 2, then let's hear Hannah's story and it will convince you.
Alright, so when I first heard of this paradox, I was really fascinated and I couldn't believe that these fractions get so small, and shouldn't just like this really small fraction, which is really close to 2, just be 2? Like,
how does it add up to 2?
Yeah, so I went on my calculator because calculators are very trusted, and I wrote down 1 plus a half plus a quarter plus a 16th and so on. I kept going up in 1 divided by 2 to the power of 1 plus 1 divided by 2 to the power of 2 and so on. And on the, I believe it was the 1 divided by 2 to the power of 32. and I clicked equals, and then it gave me the answer of 2. I was so fascinated because I thought that I had come up with an answer, and then I realized that calculators are only accurate to a certain degree.
So, for example, someone once thought that they had the solution to Fermat's last theorem. We'll be talking about that in another episode. But it's an impossible problem that has no solutions. Someone thought that they had a solution to it because they typed it into their calculator, and their calculator rounded it to 6 decimal places. But when he expanded it in a bigger calculator to get to 9 decimal places, he realized it was wrong.
So we sort of drifted off from the original problem, which is Zeno's paradox, but it's just a little bit of an interesting approach which I took on.
If anyone has a calculator with lots of decimal places, please try
this and see how far you can
see
go.
how close to 2 you can get.
Alright, so this is all for Zeno's paradox. I hope you have enjoyed and you are not too
Annoyed at us confusing
not
you.
too brain hurt.
Damaged.
Yeah, not too brain damaged as we hope. So yeah, thank you so much for watching, and we hope to see you next time. Bye.